This next section of the appendix 44.10 is on series expansions. And we really here get to see how we express certain types of values as infinite series. The most important of all the series expansions is e to the x. And you have to memorize all of the things that I'm getting ready to tell you. E to the x is, by definition, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, all the way to infinity. And of course, you're never going to add up an infinite number of terms, but these get smaller and smaller after a certain point. I might ask you a question, for example, find e to the 0.02. Well, 0.02 is very small. Certainly by the time I take it to the third power, it's going to be pretty negligible. I could even approximate it just with the first two. So to a good approximation, it would be 1.02. You can do it in your head. Incredible, huh? If you wanted a little bit more accuracy, how much more would we need to add here? The answer would be 0.02 times 0.02. 2 and 2 is 4. 000. 1, 2, 3, 4. 1, 2, 3, 4. Got it right there. So I would add to it 0.00. Oh, I've got a 2 factorial to got to add into it. So I'm going to divide that by 2 factorial. And you recall that n factorial is n times n minus 1 times n minus 2. So 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. So I divide this by 2, and I get 0.0002. And so a little bit more accurate answer would be 0.0202. If I wanted to get more accurate, I could use this term, but you can see that I'm really pretty accurate so far. So you should be able to take the exponential and take 3 terms or 5 terms and be able to compute it. And you can't use your calculator then, because your calculator is going to do it exactly. Another interesting series is the log. The log is not easy for x, but rather 1 plus x. And the log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 5th over 5. And you'll notice that there's no factorial here. In fact, the fact that there's not a factorial means that this thing is increasing pretty fast, and these have a hard time overpowering that. So x had better be not too large. However, the signs are alternating, and that does remove, let's see, this is minus, oh, this should be the 4, I'm sorry. That's 1, 2, 3, and 4. So the even terms are going to be odd sign. The odd terms are going to have an even sign. And if I have a number like 1.42, I can write that as 1 plus 0.42. Treat my x as this number here. Plug it in. You've got a very good approximation of the logarithm of 1.42. There's some other tricks you can use to find the log. Now that is a log-based e, and so normally we would write that as natural log of e. Just remember certain things when you're dealing with these series expansions. If it's an angle, use radians. No matter what it is for any function, it must be dimensionless. And the reason it has to be dimensionless is when I start taking powers, if x were measured in feet, then I'd be adding feet plus feet squared plus cubic feet plus feet to the 4th power, and there's no unit that to multiple powers will make any sense at all. Therefore, all the arguments of transcendental functions must be dimensionless. Let's use another piece of paper here. I'll call this one A and that one B. And here we have already talked about in a previous section when we talked about complex numbers, the fact that the sine of theta is by definition theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, alternating signs for all of the odd powers to infinity. You can then immediately see that the sine of a small angle is about equal to the angle itself, measured in radians. So the sine of pi over 10, well, let's take something smaller than that. Pi over 100 is going to be right at pi over 100 because these are going to be negligible in size. Likewise, the cosine of theta is by definition the infinite series 1 plus theta squared over 2 factorial, minus, plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial. And again, we're going to have alternating signs, and we're going to have all of the even powers with even factorials beneath them. It's also possible to write the sine of x, since you recall that e to the I theta is equal to cosine theta plus I sine theta. And it would also be true that e to the minus I theta is going to be cosine theta minus I sine theta. Consequently, it follows that cosine of theta times 2 is equal to, I'm adding these two together, these two cancel, and it's going to be equal to e to the I theta plus e to the minus I theta. If I divide both sides by 2, I get this equation, which is right here. If I want to do that for sine, I simply subtract this one from this one. This becomes negative, and I get the same thing. I get the sine of theta. You can do this in your head. Is going to be equal to e to the I theta minus e to the minus I theta divided by 2 and I. Because you're going to have a 2i here times the sine, so you divide through by that. Again, we have cosine squared plus sine squared is equal to 1. The hyperbolic functions are somewhat similar. The hyperbolic sine, which is, we abbreviate it in the sciences as SH, is in math often written out as SINH, the hyperbolic sine. And rather than using imaginary numbers, it uses e to the x minus e to the minus x. Notice the similarity with the cosine, or the hyperbolic, between the sine and the hyperbolic sine. Here's e to the x minus e to the minus x. Here's this. So it's as though it's a cosine of an imaginary number, which would take that imaginary I and get rid of it. And so you can think of the hyperbolic functions as sines and cosines of imaginary angles. The hyperbolic cosine is written this way. It's the sum of the two, just like the regular cosine. And these have the characteristic that the cosine squared minus the sine squared is 1. This is a very important set of functions in the theory of special relativity. And we will use those hyperbolic cosines and sines at that time. There are two other series that are important here. One of these is the binomial series. This is 4410C. The next series is the binomial series. And the binomial series says that a plus b to the nth power is a to the n. And now every time the a's and the b's multiply, but the a's reduce in power and the b's increase. There's going to be an a to the n minus 1, a to the n minus 2, a to the n minus 3. And each time we're going to have b, here's b to the 0, which is 1, b squared, b cubed. So it's very easy to see what these terms are. They always add up to the total coefficient n. Then the constants that are in front are a little bit more complicated to remember. This is going to be n. This is going to be n times n minus 1 divided by 2 factorial. This is going to be plus n times n minus 1 times n minus 2 divided by 3 factorial here, and so forth and so on. Now, the advantage of using this in all of the different sciences, whether it's chemistry, biology, pharmacy, or whatever, is what you want to do is you notice these powers of b, you would like to rig this so that b was a very small number. For example, you could write this as 1.04. What you might do is you might write the a as 1 and put, say, plus 0.04. And now a is written as 1 and b is written as 0.04. And I could approximate that by this series, and you can see by choosing a 1 here, I've made all of the powers of a equal to 1, and the powers of b get smaller and smaller and smaller very rapidly. So this is going to be approximately what? This would just be 1 plus, we could take this to some power like 3. This would be 1 plus 3 times, again that's 1, this is 0.04 to the first power, and that's probably pretty close right there. 3 and 4 is 12, 1.12. If I want to get a little bit more accurate, I would put a 3 times a 2, that's 3 times 2 over 2 factorial, and the a would have the power 1 again, because a is 1, so 1 to any power is 1. And here I would have b squared, well that's 0.04 squared, so that's getting pretty small, so I can probably ignore that. So you can see that it's very easy to take to rig the series so that the terms are very useful. What do you want to do? Make the b small. What else do you want to do? You'd like to make the a equal to 1 if you could. Well, what if you had 44 0.04? Well, one thing you could do is you could take some factor out. Like maybe you wanted to take this to some power. You could divide out something, making this a to have a value 1, and just pull that whole power to the nth power out, and then you'd be able to expand it. Of course, the greatest power of this is when these are algebraic terms. If they're algebraic terms, something like x plus uv, and you know that u and v are very small, then you'd be able to take this to the square root of this. Well, let's say 4v. And you know that v is very small, you'd be able to rig this so you could take the square root symbolically as a set of terms like this, which is much easier to deal with than the square root. Okay, so the binomial series is very useful. The Taylor series is also very useful. The Taylor series is used in calculus all the time to expand a function about a point. And f of x can be expanded so that f is evaluated at x is equal to 0, or better yet, we could evaluate it at a point x is equal to x naught. In other words, we take the function and we evaluate it at some place, like 6.3. This means evaluate the function. Plus, now that obviously the function isn't equal to just that value, but you're going to choose that value judiciously. Plus the first derivative of the function, that's equal to what? df dx. And you take that evaluated at x is equal to x naught, and normally that's written as evaluated x naught. So you just put the x naught there, and here you multiply by x minus x naught, plus f double prime 1 over 2 factorial here, evaluated at x naught times x minus x naught squared. So what you've done is you've taken an arbitrary function and used its derivatives as evaluated at some one point, like the origin or some other point that's easy or representative, and you've made that function into a sequence of a constant plus a straight line plus a parabola or a hyperbola, and you've added together all of these polynomials. And sometimes this is a very fast way to get convergence and approximation of a function in a good range. So those are two techniques that you should use also with series expansions. I've covered the other series expansions then.